Hi, this is lecture 4 for the summer session of MEC 3820 heat transfer. Just to give a quick outline, we're going to start with the conduction rate equation and develop the heat diffusion equation, which is a differential equation that will describe the conduction through a solid, and we'll then talk about the types of boundary and initial conditions that are required for this differential equation. So in layman terms, we're going to develop a physical model. We're going to convert that model into a mathematical form, i.e. a differential equation, and then we'll obtain these particular solutions that are of interest to us. So we'll start with Fourier's law, which we know as being the conduction rate equation, and we've stated that this is empirically derived. So Fourier's law gives us the amount and direction of the rate of heat transfer through a solid. In this case, the rate of heat transfer is q dot x. And notice it is a vector, and I have it being a vector in the x direction using the I unit vector. And if we then substitute in the form of Fourier's law, it's minus Ka delta T over delta x, where K is the thermal conductivity of the material. All right, so we know from the second law that heat is going to run downhill, right? So that is going to define the direction of the rate of heat transfer, so from a high temperature to a low temperature. But what we're also doing is we're defining a coordinate system. So the coordinate system is up to us, or the person solving the problem, as to which side and which direction they would want x to move, or their x coordinate to be pointing. So in this case, I have the left-hand wall marked as T1 is going to be at x1 equals 0, and the right-hand wall, which is at temperature T2, at position x2 equals L. And what we're essentially doing, right, delta T over delta x is the slope of a line. So we're going to go the rise over the run. So from T1 to T2, the rise is T2 minus T1. The run is x2 minus x1. All right, so that defines our Fourier's law for this situation. Now let's evaluate it for different cases. So for the case where T1 is the high temperature and T2 is the low temperature, that's essentially what's shown here in the figure. And we're expecting the heat rate to move from left to right in the positive x direction. Well, if that's the case, T1 is the higher value and T2 is the lower value, so the numerator here is going to be negative. But this negative value times the negative value that's included in Fourier's law makes this entire quantity positive, showing me that the heat rate is going to go in the positive x direction. Now, if we evaluate for the other situation where T1 is the low temperature and T2 is the high temperature, in that case we would expect Qx to be pointing in the negative x direction. So let's verify that that works. So if T2 is the high value minus T1, the lower value, this numerator is going to be positive. So positive times the negative will give me an entire negative quantity, which will then define the direction of the rate of heat transfer in the negative x direction. All right, so that's what the deal is with the negative sign. It's therefore making sure the direction of the heat vector, or the direction of heat is correct. All right, so let's look at a very quick example. So we have a wall made of plate glass. It's 2 millimeters thick. Plate glass, if you look in the back of the book, has a thermal conductivity of 1.4 watts per meter per Kelvin. The left-hand wall, which we'll say is x equaling 0, is the inner wall in this case, so T inner, and the surface temperature is 18 degrees Celsius. The outer wall, or T2, right, is going to be the surface temperature of the outer wall is 33 degrees. So if we want to calculate the rate of heat transfer through this solid, we'll use Fourier's law, so Q dot x equals minus Ka delta T over delta x. But we're not given an area in the problem, so we're going to utilize the heat flux. We'll take the heat rate and divide it by area, and the units will become watts per square meter. And this is the general case. If you're not given the area of a problem, for a particular problem, you divide it by a unit area, in this case 1 square meter. And your answer is going to be coming out, and how many watts of heat is transferred per unit, per square meter of the wall or the substance that you're working with. We're assuming we're assuming an infinite flat wall for most of our cases here. So negative thermal conductivity, T2 minus T1, or in this case, T outer minus T inner, and 2 millimeters, right? That's X2 minus 0. So we get negative 1.4 watts per meter Kelvin. This ends up being a positive value of 15 degrees, right? So now I'm making this kind of my own notation here, just reminding you that when you're doing a delta T, whether the units are degrees Celsius or degrees Kelvin, it doesn't matter. It's going to be the same quantity of 15 degrees. And in that case, this term here cancels with the Kelvin term that's explicitly called out when you're looking up, say, the specific heat of plate glass. Go ahead and then, of course, we got to convert our millimeters into meters to make our units work out, and we end up with a value of negative 10,500 watts per square meter, or if we want to, we could write it in terms of kilowatts. We note that the heat flux has a negative quantity, which means that the heat is flowing from the outer surface towards the inner surface, which of course makes sense since the outer surface is 33 degrees and the inner surface is 18 degrees. All right, so we have the Fourier's law, and if we, right now it's delta T over delta X, but if we allow delta X to approach 0, we get the differential equation, right? We get the derivative. So dt dx, the first order differential equation. And now we're looking at this in just one-dimensional Cartesian form if I'm only looking at the x coordinate. But in general, right, we can apply Fourier's law to a solid in 3 dimensions. And if I was going to write that in Cartesian form, that would be x, y, and z. So what we would end up in this case, we would end up using the gradient, right? So Calculus 3 rears its ugly head, right? You learn this stuff for a purpose. So Fourier's law written in flux form is minus k gradient t. And notice in this case, we're using partial derivatives, right? Because now t is explicitly a function of x and y and z. So that's very important for us to realize right now. So in the general 3-dimensional form, we have a temperature field that we would have to specify an x, y, and z coordinate and then use our solution to find out what the temperature is. And of course, if we're sticking with a one-dimensional format or a one-dimensional case, we just have temperature as solely a function of x. And that's primarily what we're going to be looking at for the majority of the problems in this class, or this first bit when we're dealing with one-dimensional conduction. So now we are saying that this derivative is going to be a derivative of a function t as a function of x. Now, I know I've stolen the thunder already by indicating that it is going to be this straight line, but we don't know at this point, right? We have this empirically derived equation, Fourier's law, and now where we originally called it delta t over delta x, but now when we say that we have to create a function, we still might know that it's T1 and T2 on the left-hand and right-hand walls, but we're not sure what the shape of the function is. All right, so that's something that we're going to be proving right now. And we're also going to have leave open the possibility of transient heat conduction. So we could end up with a case where the wall is hot to begin with, and this would be, say this is the realistic temperature profile that's existing at time t equals 0. And then as time marches on, this profile would change with time. So this would be the transient or the unsteady case. All right, so let's talk about the heat diffusion equation. So this is a type of analysis that you see multiple times in your mechanical engineering education. You should have seen it in applied strengths. You should see it when you're doing the differential analysis in fluid mechanics. So sometimes we skip that, and you're seeing it here in heat transfer. So the way it starts is we assume that we have, out of this wall where the heat is moving in this direction, we pull out a small little differential volume. And it's a differential volume in Cartesian coordinates, so the volume is given by dx by dy by dz. And if we're going to assume only heat transfer in the x direction, we will state that the heat is going to go from some x value to another x value, and it'll be passing through an area of magnitude dy times dz. Now remember, all of these terms are constants the way we're utilizing them right now. All right, so this is the simplification of my cube. I have the left-hand side is at some coordinate x, the right-hand side is at some coordinate x plus dx. On the left-hand side, we're going to say that we have energy moving in to the differential volume. On the right-hand side, at a dx away from it, we have energy moving out of the control volume. And then the two terms here are ones that we allow in the delta E, or E dot st is the stored energy. So we're going to allow for the case where energy can build up within this volume, i.e. its temperature can increase as a function of time, or its temperature can decrease as a function of time. Same thing with this red E dot g. This is going to be internal energy generation. So we're going to allow for some type of mechanism that could be a volumetric process where the energy, the volume itself at some point in time, could be steady, it could be unsteady, would be generating some amount of thermal energy. All right, so just recreating my picture over here. So in green is the rate at which energy passes into the element. In blue is the rate at which energy passes out of the element. I just want to talk about the left-hand side of this equation for right now. So if we have a certain, so what we're essentially saying here, and what we have in the back, is that this is Fourier's law, and Fourier's law can be a function of x. So we can evaluate Fourier's law at x, and we can evaluate Fourier's law at x plus dx. The red term is the rate at which energy is generated within the volume. So this is going to be the term E dot gen, little e, and this is going to be watts per cubic meter. Watts per cubic meter times the volume would give you watts. So, and the volume in this case is dx, dy, dz. Now the rate at which energy is stored within the element, well, we know that. We know the amount of energy in a volume. We gave it as m dot c sub p times its absolute temperature. So in this case, we're just going to say, well, how would that total amount of energy change as a function of time if we're allowing the element to heat up or cool down? So in this case, we'll let m be represented by rho, the density of the material. So we're going to assume a constant density material times the volume times c sub p times, now we have this derivative, dt dx, a time derivative. And notice we're going to end up, when we rearrange, we end up with a dx dy dz, and the rate that energy is generated within the element is also a function of dx dy dz. So now let's come up to this thing I skipped. What you're going to see in a lot of texts, actually it's not specifically stated in the text we're using right now, but the writers of the textbook would say that they would have this term, and then they'll write it like this, and they'll say something about using a one-term Taylor series expansion, we can allow this to be equal to that. And sometimes that is very unsatisfying, especially for an undergraduate. So I would like to take a second to take a look at what's going on here. All right. So what we're basically saying here is that if I know the value, if I know the function and I know the value at a set location, say right here, x equaling 80, and I want to know what the value of the function is over here at some 80 plus some delta x, I can either figure it out explicitly, or I can use this approximation, this one term Taylor series expansion. All right, so let's assume right now, the point is that we don't know what this function is. That's why we're using the Taylor series expansion. But what we're going to do here is just prove that this thing works. So if I have this function and I evaluate it at 80, right? So 240. And then if I say I want to evaluate it at x plus dx, I'll let dx be 5. So we would evaluate it at 85 and we get 207.5. All right, now this term over here, right, would be 240. What do we have with this term? Well, I would going to take the derivative of this function, and that's going to be 10 minus 0.2x, and I'm going to evaluate it at x equaling 80. So at x equaling 80, we end up with this term being minus 6. And then we're going to say that this term, right, I've already evaluated it at at f, the the value of the function at x equaling 85 is 207.5. But the approximation is start with the value of the function at 80, which is 240, and then add to that the value of the derivative evaluated at 80, which is minus 6, and multiply that term by this delta x that you're interested in this case is 5. So we get to 210. So for a delta x of 5, we're okay, we're in the ballpark, but we're not exactly where we'd want to be, right? So we'd say, all right, well, let's repeat this for a smaller delta x, right? Because we're not using delta x over here, we're using dx, a differential. So we repeat for delta x equaling 1, so f at 81, or so, just remember what we're doing. We know the value at 80 is 240. The value at f plus delta x is 81, so that evaluates to 233.9. So again, if I use the Taylor series approximation, the value at 80 is 240. The value of this derivative doesn't change, right? That's the point. So this stays minus 6. Now multiplying it by 5, or not 5, by our new delta x, which is 1, we get to 234. So you can see that these are very close. And of course, we could repeat this for 0.1, 0.01, etc., and that would give us a better and better value. So by using the one-term Taylor series expansion, we are able to convert this value, this term, into something that we can work with. And what do we mean by something we can work with? Well, let's go back and take a look at where we're headed with the heat diffusion equation. So we're applying the first law, so E dot in minus E dot out plus the energy generated within the element, within the volume, will have to equal the rate of change of energy within the element. So we use our colors, so E dot in is Q dot x minus Q dot x plus dx plus the energy generation term, and all of this is going to equal the rate of change of energy in the element. All right, so if we apply the Taylor series expansion to this term, which we've already done, we will get this, right? So now remember, it's a negative sign, so these two terms become negative. And, well, once we do that, these terms cancel out, all right? So now let me point out to you what we're trying to do before we go any further, right? The heat diffusion equation is going to be a differential equation in terms of T, right? So we have the temperature on the right-hand side as a function of time, but you see over on the left-hand side, temperature doesn't show up anywhere. So that's what we're working towards right now. So we have minus dq dx times dx. But what is dq dx? Well, that's Fourier's law. I can utilize, or I can take this derivative, and q dot is Fourier's law. So I can take the spatial derivative of Fourier's law, and if I substitute Fourier's law in, now we're cooking with gas. Here's our temperature term. So what we're going to get is we can take this first spatial derivative of Fourier's law. Now in this case, K is a constant. We're not allowing for variable specific heat. And remember, dy and dz, they're just differential sides of this cube, which are constants in this case. So they come out of my derivative, and I'll end up with dt, the second derivative of t with respect to x. Now notice we're writing this as a partial derivative because we know that the temperature can also be a function of time. All right, so now we're going to plug this term back in. There's a negative sign here, so the negative times a negative is going to make this term positive. And there's the dx term here, which is going to give this a dx, dy, dz, just like the other terms. So this is what we end up with. So applying the first law to the differential element, where I'll use the Taylor series expansion to give us a value, or to evaluate the rate of energy leaving the volume, and using that and then applying Fourier's law to it, we come up to this expression. Now, of course, we can cancel out the volume term across all three of the terms, and we end up with this differential equation. So I have this repeated on the next page, so let's take a look at it. So what is this? Well, this is a second order spatial, right? So the second derivative with respect to x, so that's a second order in the spatial term, and first order in the temporal term. So we got a couple things going on here. So it's second order spatial, first order temporal, linear partial differential equation. And if we can solve this, the solution will be in the form of a temperature field that gives us the temperature at any x location at any given time. All right, so just to clean it up, the textbook is a nice explanation of thermal diffusivity. So this was what's typically used when we write out the heat diffusion equation. So the thermal diffusivity is the inverse of this term here. So this becomes our final version of the heat diffusion equation, the one-dimensional form. And it's the one-dimensional Cartesian form. We're also going to have a one-dimensional cylindrical form and a one-dimension spherical form. All right, but I've just gone through the nuts and bolts of developing the one-dimensional Cartesian form of the heat diffusion equation. So we can look at a couple special cases, and so right now we, being you and us, and in your standard location where you are in your undergraduate career, you don't really have the ability to solve that type of partial differential equation, at least not yet. And at this point for our course, we're not that interested in. We want to look at some special cases. And both of these happen to be steady state. Now we are, in a couple weeks, going to come back to the heat equation, and we're going to say, all right, well, how do we solve the transient portion of it? But for right now, we're going to look at the steady state forms. So we can look just straight at the straight steady state form, which makes it equal to 0, but I leave the energy generation term in. Or the even easier or more straightforward cases, we say, all right, let's turn off any possibility of energy generation here, and this becomes our ordinary differential equation. Now, that might look familiar, but let's do a little bit more with it, right? So we have the second spatial derivative, but of course, let's rewrite what the second spatial derivative actually is, right? That says you have a function t as a function of x, take the first derivative of it, and then take the derivative of that. So what we're saying here is that the derivative of some quantity is going to equal 0. So the derivative of what yields an answer of 0? Well, the derivative of a constant is equal to 0. So that's going to tell us that dt dx, the solution, or the derivative of t with respect to x, is a constant. And this, ladies and gentlemen, that is a straight line, right? dt dx equaling a constant means that the slope is constant. So we'll come back to that in a second, but let's go ahead and talk about boundary conditions that we're going to apply to it. So the first type of boundary condition is where we would specify the temperature of the boundaries. Now again, I've mentioned this, and we're not going to worry about the mechanism by which we're specifying and holding these surfaces at a set temperature. As I said, might have to use a heating jacket and a cooling jacket that we can somehow maintain the temperatures perfectly. But this is more of a thought experiment. So if I somehow have some mechanism to keep the left-hand wall at some value t1, so x equaling 0 for all time. So I'm leaving so this is t as a function of x and time equals t1. So I'm evaluating this at x equaling 0, right? That's my boundary, my left-hand boundary. And I'm going to say that it's going to be t1 for all time. And we're going to do the same thing on the right-hand side. So this second boundary condition, right? It's second order spatial, so we need two boundary conditions. So on the right-hand side, we're x equaling L. Again, for all time, we'll specify a value of t2. And those would be my two boundary conditions. Now, the second type of boundary conditions is instead of specifying the actual temperature of these surfaces, I can specify the flux, the heat flux on these surfaces. And the heat flux is given by Fourier's law. So notice that I'm leaving explicitly the A out. So I could put A in, but we're doing this as more of a more general problem. So what I'm assuming here is that this volume, this slab, this material is infinite in this direction and infinite in and out of the board. Of course, we don't need to have them infinite. We could then say, well, we may have a smaller slab with perfect insulation around its perimeter. But in any case, we're only allowing heat transfer to move in the x direction. So we'll say, we'll use Fourier's law, evaluate it at x equaling 0, and that would give me the heat rate that's passing through the left-hand wall at x equaling 0. I would use the same value of Fourier's law, and I would evaluate it at x equaling L, and that's going to give me the heat rate that's passing through the right-hand wall. So there's another set of boundary conditions. And of course, we can mix these boundary conditions. I could say that this wall is a constant temperature, and this wall has a heat flux on it. So these are things that we'll be looking at when we look at actual problems. So now, we're still in the type 2 boundary condition, but there's some variations that we can look at it. If this surface is next to or is completely insulated, we do not allow for heat transfer across this boundary. So the heat flux, Q dot, is going to be equal to 0. So in that case, that would be one variation of the heat flux boundary condition. On the right-hand side, or the other side, we could allow that the rate of heat transfer is going to be exactly matched by a convective, I guess I can call it a convective boundary condition, but it's going to be defined by the convective situation that exists outside the wall at x equaling L. So to utilize this, we would typically you would need to be specified what the heat transfer coefficient is, H, and what the infinity temperature is. But again, we'll be taking a look at it, but it's just two variations on how we can utilize the heat flux as terms of a boundary condition. All right, so I just want to quickly go through one example. This is an example from another textbook, but I do like this type of example because it allows us to sort of manipulate what the heat diffusion equation is to a certain extent. All right, so what we're being told here is that the temperature distribution across the wall that's 0.3 meters thick at a certain instant in time. Now that's important. When you hear a term saying at a certain instant in time, the implication is that something will be different at another instant in time. So what they're implying here is that this is an unsteady problem. But we can still utilize the heat diffusion equation. Well, the heat diffusion equation is inherently for the unsteady process. Let's see where this is going to take us. It tells us that the temperature distribution is this quadratic. A, the constant, is 200 degrees C. B, the linear term, is minus 200 degrees C per meter. And of course, you're going to multiply it by meter, the x value. So this is again going to have the units of degrees centigrade. And the quadratic term is 30 degrees centigrade per square meter, which again, you're going to be multiplying by a square meter. So that makes perfect sense, right? The temperature field has the units of degrees Celsius. So what I'm going to do over here is this diagram is the diagram of the actual physical situation. So it's being plotted from x equaling 0 to x equaling 0.3. I'm evaluating the temperature at x equaling 0 using this equation, and I get 200 degrees C on the left-hand side. And on the right-hand side, I get the value of 142.7 degrees C. So this is just a cautionary to you. So a lot of you would say, oh, it's quadratic, and automatically you see a parabola in your head. But what we're finding out here is we're actually on, right, it's parabolic, right? It's the A term is, the C term is positive. So it's a upward parabola, but we're way over on the left-hand side, way far away from the minimum of the equation. All right, so what we see is that it's almost linear, but it's not linear. So now I've put these in a priori before I've evaluated them, but what I'm assuming here is that when I evaluate Q in or Q dot at x equaling 0, I'm going to get a positive value. So the heat's coming into the left-hand wall. I'm also drawing the heat flux on the right-hand wall as being also going from left to right. So in this case, I'm also assuming it to be positive, but a positive value for the heat flux at the right-hand wall means that we're having heat flowing out the right-hand wall. which of course will make sense because look at the heat profile. We're expecting a heat profile where energy is kind of flowing downhill. So this is our equation. If I take the first derivative of it, it's going to be minus 200 plus 60x, and of course it's dt, right? So the numerator has units of temperature, degrees C. Denominator is dx, so units of meters. And now I can evaluate, if I know dt dx, I can evaluate the flux using Fourier's law. So minus K is 1 watt per meter per Kelvin, and here is the term dt dx, right? dt dx now is an actual function. And if I evaluate it, my degrees C, right, this is a temperature differential. So degrees C and degrees Kelvin are going to cancel out. I'm actually going to come back to that tomorrow in class. There's this can actually be a little bit confusing for you, why I can cancel these two out. So I have a little explanation that we'll do in class. And this will end up with watts per meter squared. So 200 minus 60x, watts per square meter. And the question is this a steady state situation? Well, we don't think so, because we know this isn't linear, even though it's almost linear, and we have this hint that at a certain instant in time, it's implying that there's something happening with regards to time. All right, so let's go back. Let's go take a look now. So if I evaluate, here's my expression for Q dot as a function of x, 200 minus 60x watts per square meter. If I evaluate this at the left-hand wall at x equaling 0, I'm going to end up with 200 watts per square meter. So the left-hand wall, right, and this is positive, so the left-hand wall, Q dot in, is 200 watts per square meter. The right-hand wall, if I evaluate it at x equaling 0.3, evaluates to a positive 182 watts per square meter. So that means that I'm also in the positive direction, but this is causing energy to leave the wall, and it's at 182 watts per square meter. So they're not equal to each other. The first law says that the rate of change of energy in the element is equal to En minus E out plus Eg. Well, the problem doesn't provide us with any information about volumetric heat generation, so we're going to assume that's 0. And so what we end up with is 200 minus 182 plus 0 equals 18 watts per square meter. So what that's basically telling us is that the amount of energy within every 1 square meter of the wall is increasing at 18 joules per second. Now I want to be very clear about this. For this wall, we're assuming I'm taking 1 square meter of the wall, but that 1 square meter is 0.3 meters thick. So if you were going to calculate a volumetric energy rate, it's not per 1 cubic meter, it's 1 square meter times 0.3. So it's 0.3 cubic meters. So within every 0.3 cubic meters of this wall, the wall is increasing, the temperature or the energy in the wall is increasing at a rate of 18 joules per second. All right, so just be clear on that. Now, the last thing it says is that the cold surface is characterized by a convective boundary condition. So what they're telling us is that the outside surface, the free stream condition is 100 degrees. So we have that. We have T2. Right? We know what the wall temperature is on the right-hand wall, and we know how much energy must be going out the right-hand wall, or has to go out the right-hand wall. So I can rearrange this, and the only unknown here is my heat convection coefficient. So I'll rearrange it, and I'll find out that for this situation, if it was happening at this instant in time, the heat transfer coefficient would have to be 4.26 watts per meter squared per Kelvin. All right, so that gives us a kind of a quick overview of how Fourier's law is used to allow us to create the heat equation, which is a second order in space and first order in time differential equation. And we've looked at applying boundary conditions, or at least just the boundary conditions. So it's a second order spatial, so we need 2 boundary conditions. And we've looked at least one example of the steady state case.